بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. Good morning, dear students, and thank you for joining this lecture in which we will explain the main differences between grid and cloud computing and also their related services. So, before starting this lecture, normally you are expected to be able to, through this lecture, to explain the hardware layer in cloud computing, define the relationship between grid and cloud computing, distinguish between grid and cloud computing, and finally, determine the major cloud providers. So, before talking about the hardware layer in any cloud computing, it's advisable to make a reminder about the OSI model or the OSI layers. The architecture of a network is defined by the set of layers and the description of the protocols and services of each of them. As you know, the OSI model has 7 layers. Just I wanted to make the slides in full screen. It's okay now. So, the first layer is about the physical layer, which is layer 1. This layer, in fact, provides the mechanical, optical, electronic, functional, and procedural means necessary for activating, maintaining, and deactivating the physical connection necessary for the transmission of bit streams. The layer number 2, which is the data link layer. This layer ensures the transmission of information between 2 or more immediately adjacent systems. It also detects and corrects, as far as possible, errors originating from the lower layer. So the objects exchanged are often called frames. The layer number 3, which refers to the network layer. This layer carries information across a network that may consist of intermediate systems or routers. So the objects exchanged are often called packets. Layer number 4 is the transport layer. This layer ensures end-to-end transmission of data. It maintains a certain quality of transmission, particularly with regard to reliability and optimization of resource use. The objects exchanged are often called messages. Layer number 5, which is the session layer. This layer provides cooperating entities with the means necessary to synchronize their dialogues, interrupt them, or resume them while ensuring the consistency of the data exchange. Layer number 6, which is about the presentation layer. Presentation layer is responsible for representing the information that the entities exchange and hides the heterogeneity of coding technique used by the different systems. The last layer, which is layer number 7, refers to the application layer. This layer gives application processes the means to access the OSI communication environment. It includes many protocols adapted to different application classes. Here, it's important to mention that the local functionalities of the application themselves are outside the scope of the OSI and therefore of the application layer. So, as conclusion, the first 3 layers constitute the low layers where the constraints of the network are perceptible. The transport layer is adaptation or intermediate layer, most often associated with the low layers. The last 3 layers constitute the high layers where the constraints of the application are perceptible, complex and variable functions adapted to application processing. The standard clearly states that this is a reference model and therefore, depending on the context in which we find ourselves and the communication needs, certain functionalities of certain layers may not be used, such as the alternative protocols, protocol classes, options, etc. So this is a gentle reminder about the OSI layers or the OSI model. Now, let's explain the server or the rack server. What is a rack server and how to choose it? As you know, in the world of IT infrastructure, the need for space optimization and operational efficiency is crucial. And this is where the rack server is a fundamental element of data centers. It is designed to be mounted in standardized cabinets. So this type of server maximizes spaces and facilitates system management. What is the utility and composition of rack server? A rack server is a computing unit designed to be installed in a standardized server bay or rack cabinet. This configuration facilitates space management and the organization of IT components within companies. This format allows rack servers to be stacked on top of each other in a configuration that optimizes the use of vertical space. Typically, each rack server is measured in rack units with the character U, with each unit equaling about 1.75 inch of height. The components of a rack server include the usual elements of a computer server, including motherboard, processor, RAM, storage with hard drives or SSDs, as well as systems for power distribution and cable management. In fact, businesses favor rack servers for their modularity and ability to easily plug into a complex cable management and power distribution system. Now, let's explain or let's highlight some benefits of rack servers for businesses. So, businesses that adopt rack servers benefit from advantages that are conducive to the performance and scalability of their IT network. First, consolidating servers in a single location allows for significant space saving, especially relevant for data centers where floor space is a significant cost factor. Organization and accessibility are also greatly improved with rack server. Rack cabinets allow for orderly management of servers and cables, which minimizes the risk of damage and facilitates maintenance and upgrade operations. In addition, the storage capacity and computing power of rack servers are assets for companies processing large volumes of data. Generally, rack servers support high-density storage solutions and offer high computing power. Now, how to choose the right rack server? And this is an important question. So, selecting the ideal rack server requires precisely defining your company's needs in terms of data processing, web applications, storage, bandwidth, and IT services. Since each company has unique needs, several factors must be taken into account when choosing a rack server. So when choosing your rack server, you must consider both the expected storage capacity and the requirements in terms of computing power and data redundancy, and also cooling solutions and network connectivity needs. Now, how to install and configure your rack server? Installing and configuring a rack server requires careful planning to ensure that all components work together. This starts with choosing the right server cabinet and considering power distribution and cooling systems. So, standardizing cabinets into rack units with a U format makes it easier to match and arrange different equipment. The configuration of the rack servers themselves will vary depending on the storage, data processing, and service requirements to be deployed. So, choosing the right type of server, whether application-specific storage or high-performance computing, is very important. Installation also involves integrating into the company's existing network, ensuring compatibility and securing data flows. Finally, technical support can be essential for configuring the network infrastructure, including the IP addresses, gateways, and network security setting to ensure that the system operates optimally. So, regarding rack servers or servers, we have two kinds of servers: rack server and tower server. What is the difference? Rack servers and tower servers are two different types of computer servers. For the tower servers, they are similar to traditional desktop personal computers in that they are designed to sit on the floor or on a stand. Their design makes them more suitable for small businesses that do not necessarily need a large number of network machines. Tower servers often have fewer customization and expansion options than rack servers. On the other hand, rack servers are designed to feed into a standardized network rack. This is in order to build a stacked server infrastructure that is optimized for space. This arrangement is therefore better suited for environments where the aim is to maximize server density and efficiency in managing IT resources. In terms of power and capacity, racks serve more intensive applications and are therefore a preferred choice for data centers and large enterprises. Now, let's explain the main differences between grid and cloud computing regarding some defined criteria, which are objective, calculation access, workflow management, discovery, resource management, allocation scheduling, interoperability, level of abstraction, degree of scalability, multitasking, transparency, execution time, allocation unit, virtualization, accessible portal, security, operating systems, fault tolerance, price of services, ease of use, type of service, response time, critical object, number of users, resources configuration, and so on. So, before talking about the difference between cloud computing and grid computing, it's important to make some reminders about what is the grid computing and cloud computing explained in the previous chapters. The architecture of cloud computing comprised two distinct parts: the front end and the back end, which communicate via the internet. The front end encompasses client facilities such as user interfaces, user-side applications, and client networks or devices, enabling users to access and use cloud services. On the other hand, the back end encompasses all the elements involved in establishing the cloud infrastructure, including management, security, computing, and storage resources. So all components of cloud architecture collaborate to provide the foundation for cloud computing, offering users on-demand access to a variety of services and resources. The front end communicates user interaction to the backend through middleware, where the application's service model executes requested actions. As cloud strategies evolve, The expertise of cloud architects becomes increasingly vital as they assist businesses in navigating the complexities of cloud environments, implementing effective strategies, and ensuring the seamless operation of the cloud infrastructure. This is for the cloud computing. Here it's also to mention or to highlight some advantage and disadvantage of cloud computing. Let's start by the advantage of cloud computing. First, one of the advantages of cloud computing is scalability. Second, cloud computing provides on-demand service. Three, cloud computing is cost-effective. Four, cloud services are accessible from anywhere with an internet connection. And finally, cloud computing provides rapid elasticity. This is some advantage of cloud computing. Now let's explain some disadvantage of cloud computing. First, its dependence on internet connectivity. Two, security concerns. Three, cloud computing requires constant and high speed internet. And finally, users have less control over the underlying infrastructure and configurations. So this is about cloud computing. Now, let's make a reminder about grid computing. Grid computing operates on the principle of resource sharing, allowing organizations to tap into underutilized computing power across their network, effectively creating a virtual supercomputer. This approach is highly scalable, making it ideal for handling tasks that demand significant computational resources, such as scientific simulations, data analysis, and large-scale simulations. So a key feature of grid computing is its ability to handle diverse workloads and allocate tasks dynamically by enhancing overall efficiency. Grids are commonly used in scientific research, engineering, and industry, requiring extensive data processing, enabling more efficient problem solving and resource use. So, grid computing has paved the way for cloud computing and plays a crucial role in addressing complex problems in our data-driven world. Now, since we have a lot of criteria, which are about maybe more than 20 criteria, I think it's important to summarize the differences between grid and cloud computing on some essential criteria or aspects such resource ownership, scalability, cost model, workload type, location independence, resource heterogeneity, resource use, deployment and maintenance, accessibility and security. In fact, for the first criteria or the first aspect, which is the resource ownership, in grid computing is a diverse organization. In cloud computing is a cloud service provider. What we mean by resource ownership? Grids are typically composed of resources that are owned and managed by various organizations. These resources can be geographically dispersed and can vary significantly in terms of hardware, software, and configurations. The coordination of tasks and data sharing in grid computing often involves complex negotiation and agreements among resource owners. For the scalability factor or criteria or aspect, in grid computing is limited with or within federation. But in cloud computing is elastic and on demand. What we mean by scalability? Grids are designed for high performance and data intensive computing, often for scientific research and technical applications. They can accommodate large-scale computation, making them suitable for projects that require significant processing power and storage capacity. However, scalability in grid computing can be challenging due to the diversity of resource and the need for resource management. Clouds are highly scalable and flexible, with the ability to allocate or reallocate resources on demand. Cloud providers offer a range of service models, including infrastructure as a service, platform as a service, and software as a service. This flexibility allows cloud computing to cater to a broad spectrum of applications, from small-scale web hosting to large-scale data analytics. The third criteria, which is the resource sharing. For the resource sharing, grids are founded on the principle of resource sharing among multiple organizations and research institutions. So collaboration and data sharing are fundamental to grid computing, with tasks often distributed across different administrative domains. This makes grid computing suitable for collaborative, data-intensive projects such as climate modeling and particle physics. Cloud computing, on the other hand, is primarily designed to provide services and resources to end users and businesses. So, resource sharing is limited to the cloud provider's infrastructure and is typically not extended to other organizations. So cloud services are more focused on delivering applications and services directly to users. For the cost or the cost structure criteria, in grid computing is a complex resource based, but in cloud is pay as you go and predictable. For the service or the cost structure in grid computing can be intricate, involving negotiations and agreements among organizations participating in a grid. This organization may share the cost of infrastructure, maintenance, and resource usage, making grids suitable for long-term, large-scale projects. The financial model can be project-based or collaborative, depending on the specific needs of the participants. Cloud services usually follow a pay-as-you-go model, where users are billed for the resources they consume. This cost structure is well suited for businesses with variable workloads, as they can scale resources up or down as needed. Also, optimizing costs. So here, users are only charged for the services they use, providing cost effectiveness for a wide range of applications. For the service models criteria, in grid computing primarily focuses on compute and data intensive tasks. So users often have to manage the resources and tasks themselves, as grid provide a more low-level infrastructure. Grid computing is commonly used for specialized research and scientific applications. Clouds offer a wide array of service models, including infrastructure as a service, platform as a service, and software as a service. For the infrastructure as a service, it provides virtualized infrastructure. For the platform as a service, it offers platforms for developing and deploying applications. And for the software as a service, it delivers complete software solutions. So users can select the service model that best matches their specific needs, simplifying the deployment and management of applications and services. For the elasticity criteria, grids typically like the automatic scalability and elasticity found in cloud services. So users often need to manually allocate and manage resources, which can be complex and time-consuming. This manual resource management makes grid computing less agile in responding to fluctuating workloads. Clouds are known for their automatic scalability and elasticity. So resources can be provisioned or deprovisioned based on demand, allowing users to adapt to workload fluctuation efficiently. This elasticity contributes to cost efficiency and flexibility, making cloud computing particularly attractive for businesses with variable resource requirements. Here we are also some other criteria. For example, for the calculation axis, in grid computing is an intensive computing operations. For cloud is a standard and high-level instances. For the workflow management criteria, in grid computing is on a physical node, but for the cloud computing is in the EC2 instance, Amazon EC2 plus S3, which has been explained in chapter 4. For example, for the allocation or scheduling in grid computing is decentralized. But in cloud computing is both centralized and decentralized. For example, for the interoperability criteria, in grid computing is based on grid standards. But in cloud computing is based on web services, such SOAP and REST. For the level of abstraction criteria, in grid computing is low, with more details. But in cloud computing is high, and there is no details about the level of abstraction. For the multitasking is permitted or allowed both for grid and cloud. For the transparency, in grid is low, but in cloud is high. For the execution time, in grid computing is not in real time, contrary to cloud computing, which is in real time. For the allocation unit in grid computing is based on small tasks. But in cloud, all kinds and sizes. For example, for the accessible portal, in grid computing is done via a DNS system, but in cloud computing is via IP only. For the owner, for example, is multiple in grid computing and unique in cloud computing. For the fault tolerance, which is limited in grid and strong based on migration processes in cloud computing. So this is the main or the differences between cloud and grid based on the main criteria. You have also here some other criteria. So in conclusion, both cloud computing and grid computing use distributed computing resources. Cloud computing provides scalable on-demand service with a focus on accessibility and cost efficiency, making it suitable for a wide range of applications from personal to enterprise. Grid computing, on the other hand, performs well in contexts that require high performance computing and resource sharing across different domains, such as scientific research and complex computations. So, understanding these characteristics helps in selecting the best technology that meets certain computing needs and goals. Here we have also, let's talk now in the second part of this chapter about some major cloud providers, such as Amazon Web Service, Google Cloud Platform, Microsoft Azure, IBM, and Salesforce. Okay. So mainly we will focus on the AWS which is the cloud provider which is the most used in the world, and we will see that in the second part of this lecture. Thank you for your listening. Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh.